and 0.32 grams of oxygen, and it adds what was the empirical formula. I don't know who was it who volunteered. Was it you, Brian, that volunteered?
Nah, I ain't volunteer.
Okay.
I mean, I'll attempt it. I forgot how to do it a little bit.
All right. Well, we'll take that. Let's just. I can. We'll put it on the screen. Tell me what's the first thing you'll do. Now we have our given masses, and we know our atomic masses. We're trying to calculate the empirical formula. So tell me what's the first thing you do with those masses that are given. Stop.
Don't you find the mass of like the element and then you multiply it by whatever number it is?
Okay, so I'm with you. So you're saying find. Sorry about that. The atomic mass of each element.
Yes, sir.
All right, I'm with you on that. So for nitrogen, it is 14 grams per mole. And then for oxygen, it's 16 grams per mole. So you're right about that. All right, so what we're trying to do when we're calculating empirical formula is to find anybody, help me out. What are we looking for? We're looking for the mole to mole ratio. So now let's go back to what we got, Brian, and tell me how you would figure out the number of moles of nitrogen given what we have. We got 0.13 grams of nitrogen right here, and we also have the atomic mass of nitrogen. So how can we find the moles of nitrogen?
Just to make sure I ain't tripping, will we multiply the atomic mass times the gram?
Okay, if you multiply them, then you would get grams squared, and you don't want that. So you actually divide them. So it's grams over molar mass, which is going to give me moles, right? So I'm going to take that number, 0.13 grams of nitrogen, and divide it by 14.0 grams per mole. That way grams will cancel instead of doubling. Does that make sense? So then I'm left. Go ahead and punch that in, somebody, or if you got your calculator handy, go ahead and punch that in. Point.
I got 0.009.
All right, 0.009, which we can round up to 0.01. Good. 0.01. And this is moles. All right. Now, how do we get the next one? Are we going to do something different? Or are we just
No,
going to
it's the same thing, ain't it?
same thing, just swap the numbers out? All right. So it's going to be 0.32 grams divided by 16 grams per mole. Go ahead and calculate that.
0.02.
So 0.02 moles. All right, what's next? So we found the moles using the given mass and the atomic mass of each element. So now we can write this like this, and we'll put those mole numbers down here. Is that right?
Wouldn't you divide both by the lowest number of moles
Yes, sir,
you
we
can get?
would. That's exactly right. So now we can do that. And this divided by 0.01. So what am I left with?
NO2.
NO2. Good. This is the empirical formula for this sample that contains 0.13 grams of nitrogen and 0.32 grams of oxygen. Excellent. Nice work. Any questions about it? All right. Let me just stick a date on here. And so now we're going to take this empirical formula information. We're going to do a couple more examples with calculating empirical formula, but we're not using the we're not going to use the masses. We're going to be given percent composition. So today, those are the examples that we're going to be doing. All right, we're going to take. It's not a preference. You're fucking right. Hold up. All right. So instead of taking the given masses and atomic masses, we're going to start out using percent composition. So that's what we're going to be at. That's what we're going to start with today. Because we know how to calculate empirical formula. But what if we're not just giving masses? What if we're given the percent composition? Then we have to, there's another route to determine an empirical formula using the percent composition. So we're going to find out if percent composition is given, we can derive the masses. All right, we can derive the necessary info. And this is a kind of a preview of some other problems that we're going to be working with molarity, in that sometimes you have to make an assumption about what you have in order to determine some variable or some number that you actually need. So you have to derive it. So we're going to work backwards. So we're going to retroactively determine the masses. Right, using percent composition. Right, so let's take this first example. And for this, we got a sample gas. And this gas has a percent composition of 27.29% carbon and 72.71% oxygen. Right? So, and the question is, what is the empirical formula? So we can figure that out. Remember, all the stuff we did on Friday, calculating empirical formula, what we did was we took a given mass divided by atomic mass to find moles, right? And then we took those moles and put them into an equation like this, right? Where we have the element, but once we find the moles, we put them into this equation and then we divide by the lowest number. So these are the steps. So we find the moles. Use the moles here and then divide by the lowest number. Same thing we just did on the previous example. Come on, Russell. Right. So what we have here, we don't have the masses, but we have the percent composition. Anytime you have percent composition, it always has to add up to 100. Right. So if you got 10 atoms, the percentages of those atoms must add to 100%. Right. So with a problem like this, where you just have percent composition, right, the approach to it is to first assume 100 grams, right? If percent composition, if only percent composition is given, right? You assume 100 grams of product because again, the percent composition has to add up to 100. All right. So we look at this compound and it tells us that it's 27.29% carbon and then 72.71% oxygen. We could just take those numbers and say, okay, if it's 27% carbon and it's a 100 gram sample, that means 27.29 grams of carbon. And it also means 79.21. No, I was right the first time. 72.71. Come on, Russell. 72.71 grams of oxygen. Right? So it's a 100 gram sample. So that's those two total up to 100. So now what can we do? We've taken the percentages and turned them into mass amounts. So now these are our given masses. So now all we need to do is do what? We're going to find the number of moles.
Don't we gotta never mind. Go ahead.
Go ahead. No, go ahead.
I was gonna ask if we had to divide the moles by the atomic mass.
Yes, sir. That's exactly what we're doing for both of them. So that's going to be for carbon, and then this is going to be for oxygen. All right. Go ahead and calculate that. Tell me what you got. So again, if we don't have masses, but we have percent composition, we can work from the percent composition to determine the masses. And then once we get the masses, we can figure out the moles. And the rest of it after that is just it's all academic after that. Go ahead. What we got for that first number? 27.29 divided by 12.01.
2.272.
Let's round that down to 2.27. And then what about the second one?
4.54.
All right, 4.54 moles. All right, bet. So now we're good. Now what's next? We got them. We took the masses. We got the moles. Now we want to set this equation up where this is C and O, and we need to put our moles here, right? 2.27, 4.54, and then now what?
Divide by the lowest.
Divide by the lowest one. I'm gonna divide by the smallest number, which in this case is 2.27. And then so now my empirical formula is CO2. All right. So this is the empirical formula for a sample that has a percent composition of 27.29% carbon at 7.772 points. That's kicking my behind today. 72.71 grams of oxygen or percent of oxygen. Right. So for problems like this, when you're given the percent composition, what you're doing is you're going to have to first convert that into grams. And the way you do that is to assume that the sample is 100 grams because your percentages all have to total up to 100. All right. Any questions? Any questions about that? All right, let's do another one. Let's take this second example. And let's say we have a sample And again, we're going to be given the percent composition. A sample that's 40% carbon, 6.71% hydrogen, and 53.28% oxygen. Right, this is our percent composition. Right, and we want to find out what the empirical formula is. Right, what are my steps if I'm starting from percent composition?
You want to use the grams and divide it by the molar mass.
Good. So we're going to take that percent composition to find the grams, right? And then we're going to do what you just suggested, which is to use the masses to find moles, right? By dividing what? Grams over molar mass, which in this case, we're going to be using the atomic mass of each element, right? And then then we're going to set up our chemical formula with moles as the subscript. And then, of course, we're going to divide by the smallest number. So what we're always trying to do is have a strategy based on what's given. So if we're talking about empirical formulas and all we're given is percent composition, this is our strategy. Take the percent composition, take those numbers, turn them into grams. Assume that the sample is 100 grams. Take the masses, find the moles, plug the moles in as subscripts in a chemical formula, and then divide by the smallest number. So let's take it. So this sample is 40% carbon, 6.71% hydrogen, and 53.28% oxygen. So we can look at it like this. This is 40 grams. I'm going to assume 100 grams. So that's 40 grams of carbon. That's 6.71 grams of hydrogen and 53.28 grams of oxygen. Right, and each one of these we're going to divide by its atomic mass, by the atomic mass of the element, but we're going to put it in grams per mole instead of AMU. This is 12.01 grams per mole. This is 1.008 grams per mole, and then this is 16 grams per mole. All these numbers on the bottom are taken directly from the periodic table. All right. So what is that? How many moles of carbon is that?
.33.
All right. So 3.33 moles of carbon. What about hydrogen?
What's the grams per mole number? Like, what is
For
that
hydrogen?
1.00? What's the, there's an 8?
Yeah. 1.008.
It's 6.65.
All right. 6.65. Is that rounded down or up?
Down. So yeah, you can round it up to 6.6.
All right, we'll leave that. We don't worry about it. All right. Now, what about oxygen?
Is that 53 or 55?
My bad. It's 53.28.
It's 3.33 again.
All right. right? So those are our numbers. So now we can set up our chemical formula, right? CHO, and this is 3.33. This is 6.66, and this is 3.33. Now what?
Divide by the lowest.
Divide by the lowest one, which is going to be 3.33. That's going to cancel. That's going to cancel. And then this will divide down to 2, right? So that's going to be CH2O. Right. And this is my empirical formula. Right. So again, we can calculate or determine the empirical formula based on 2 methods. One, if we're given the masses, we can find the moles and just set up the chemical formula and plug those numbers in and divide by the lowest number. The other way is to take a percent composition and then from that derive the masses and then use those masses the same way. From that point, it's the same. Find the moles and then plug them into your chemical formula and then divide by the smallest number. So it's the same in both cases. All right, so now let's go to, let's switch gears for a second. And we're going to talk about now how to use empirical formula to calculate or determine molecular formula. So we're going to determine, again, molecular formula from empirical formula. Right. And there's the reason why we have to do this is because, remember, the empirical formula is not the actual molecular formula, is not the exact amount of atoms. It's a relative amount of atoms. So it's like the reduced form of the molecular formula. So it's a relative number of atoms. We've also referred to it as the reduced form of the molecular formula. And so in order to take the empirical formula and find the molecular formula, we need what's called the number of formula units. And this is, it sounds like a lot, but it's not as bad as it sounds. So to convert empirical formula into molecular formula, we need to find N, which is the number of formula units. So we have to find that number. And it's not difficult to find. The way we find that formula unit number, right, is very simple. We're going to take the molar mass divided by the empirical formula molar mass. Right, that's how we're going to find N. So once we find N, it's just a matter of taking that. And then let's say this is my empirical formula AX BY. When I find N, I'm going to distribute that through here. So I'm going to distribute it here, wrong pen, and here. But I have to find it first. So this is my empirical formula. And then when I find N and distribute it, this is going to become my molecular formula, right? So N is findable, right? Empirical formula is findable. Either we're going to have masses or we're going to have percent composition. We can find the empirical formula. How do we calculate molar mass? Anybody remember? What do I need? Isn't it just the sum of all the atomic masses? Right. If I have a compound, if I have a formula, or if I'm given, I can also find the molar mass if I'm given a certain number of grams and the number of moles that grams is equivalent, that number of grams is equivalent to, I can find it that way too. Right. But let's do an example, and this will bring all this kind of full circle. Right. So we got an example here. Right. Any questions about this so far? So now we're going to use empirical formula to determine molecular formula. Once we do, and once we know the empirical formula and the molar mass of the molecular formula, we can find out N, which is formula units. And once we do that, we're in the clear. All right. So let's do this example right here, and then we're going to walk it down. No matter what's presented, we can always walk it down. All we need to do is take the same strategy we always take. Find out what we have, find out what we need, right? So take the given information, and then from that given information, we're going to determine what we need, right? And from the given information, we may be able to derive some other information that's not given. So all of that is going to come into play in this problem right here. So we got a sample of nicotine. Right. This is the addictive component of tobacco. I'm sure you already know that, but this is, and so we have a sample of nicotine, and it is 74.02% carbon. It is 8.710% hydrogen. And it is 17.27% nitrogen. What can we find from that? This is the percent composition. What can we use this for? What do we use it for up here?
Find we converted each of them to the mass and then divided them to get the percent for each, or the weight of each atom, and divided that by the molar mass to get the total
moles, right? So if we're given, this is the given information for this problem. First thing they give us is the percent composition. So from this, we can find the empirical formula. We can use that to find the empirical formula. Then it gives us another piece of information. It says that 40.57 grams of nicotine is 0.25 moles. What can we get from that?
an entire mole of nicotine, or how many grams are in 1 mole of nicotine?
Exactly. So we can actually get the molar mass of nicotine from this. All we have to do is take 40.57 grams and divide it by 0.25 moles. And that's going to tell us how many grams are in 1 mole, which is the exact same thing as the molar mass. Somebody go ahead and calculate that.
162.28.
162.28.
Yeah.
And this is in what? Grams per mole. Excellent. Nice work. All right. So we got a lot of information. So let's hold on to that molecular weight or molar mass. Let's hold on to that because we're going to need that later. But first thing we need to do is to find the empirical formula. That's the first thing that we're going to do here. Somebody help me set this up using the percent composition, right? What can we say about the percent? First of all, we can do what? Because it's in percentage, we can assume what? How much?
It's 100 grams
Is that
total.
100?
100 grams. Yeah, because it has to add up to 100%. Yes. Right. So then we got 74.02 grams of carbon. We got 8.71 grams of hydrogen. And then we also have 17.27 grams of nitrogen. Now we're going to just take these and do what? Divide them by what?
The molar mass.
Atomic mass.
Yep. Grams per mole. And this is 1.008 grams per mole. And this is 14 grams per mole. All right. Can we get somebody to calculate that? One person calculate each one.
The grams or the moles for carbon are 6.16.
Okay. So 6.16.
Hydrogen is.
Go ahead.
Go ahead.
Go ahead.
I was gonna say that hydrogen is 8.64.
All right. 8.64 not grams, sorry, moles. Hydrogen. What about oxygen? Somebody got that one?
1.23.
Excellent. 23 moles of nitrogen. I think I said oxygen. My bad. It's nitrogen. All right, great. So now, once we have these numbers, what can we do? We
The lowest.
put them in a chemical formula. We can set up the empirical formula, can't we? We say C is 6.16, H is 8.64, and then N is 1.23. What are we going to divide by?
The lowest.
Lowest one, which is 1.23. All right, what do we have for the empirical formula? What is that? C what?
Is it 5?
Okay, C5, we'll take that. H what?
That's 7.02. Just leave that at 7.
We will leave it at 7. Yep. And then N, this is assumed to be 1 if there's nothing there. So it's N1, right? All right, so now we have our empirical formula. And let's go back up to our equation to find formula units. We need the molar mass and divide that by the empirical formula molar mass. So let's calculate. We know what the molar mass is. We've already found that, right? We took the 45 40.57 and divided it by 0.25 moles. So we got that number. Let's find the empirical formula molar mass. Right, and all we're going to do is take this formula right here, and we got 5 carbons, we got 7 hydrogens, and we got 1 nitrogen. And then we're going to sum it all up. So this will be 60.05, and this is in grams per mole. And this will be 7.056 grams per mole, and then this is 14 grams per mole, and we just sum it, and that's going to be our molar mass for the empirical formula, right? Which in this case is going to be 81.106 grams per mole. Any questions so far? All we're doing is taking stuff we already know how to do. We've done empirical formula already. We've used the percent composition to find empirical formula. We've done all that, right? So now, and then we've also done molar mass. That's the first thing we did in this section, taking all the atoms and atomic masses and adding them all together. So now we know our empirical formula molar mass is 81.106. And we already know the nicotine molar mass. We got that up top, which was 162 point, what was it? 162.3. Yeah, 162.28. Right, so we already calculated that. So now we just need to find formula units. Find N. And we're going to take that number, 162.28, and we're going to divide it. So this is the molar mass, and so this is the compound molar mass. And we're going to divide that by the empirical formula molar mass, which was 81.106. And this is in grams per mole. This is in grams per mole, so they're going to cancel each other out. What do you have? What do we have for that?
2.
2. Good. So N is 2. All right. Once we do that, the last step is to distribute this through the empirical formula, which we found up here. So we're going to take that empirical formula C5H7N and put a 2 out here, and we're going to distribute that to each term. Basically multiply each term by 2, each subscript by 2. So the molecular formula so the molecular formula is going to be C10 H14 N2. Anybody not following or not catching it or not seeing what we're doing? Again, we are using the empirical formula to determine the molecular formula, but we're not just given the empirical formula, we're given percent composition. And then based on that, we use that to find the empirical formula, right? And then we're also given a molar mass. We need both of those in order to do it this way. Or we need the terms for each so we can find each one. All right. So now let me give you a snapshot of this, what it actually looks like. So this is nicotine. I pulled it up this morning, but I can just draw it. So this is the structure of nicotine. It looks like this. All right. And then it has a carbon right here with 3 hydrogens on it. Now on the ring, everywhere you see 2 lines coming together like this, these are carbons, right? Unless it's otherwise noted, like this is a nitrogen right here. So, but every place you see a vertex, 2 lines coming together like that in that ring, that's a carbon. Same thing over here. And then this is obviously a carbon because you have it drawn out. So how many carbons is that? Let's count them up. So it's 1, 2, 3, 4, 5, 6, 7, 8,
Yeah.
10, right? So that part we've proven that it's C10. All right, now on the ring, everywhere that there's no atom indicated, there's a hydrogen. So this is H, this is H, this is H, and that's H. Right, so there's 1 hydrogen on each one of these carbons. And then over here, there are 2 hydrogens on each one of these carbons because the carbon can make 4 bonds. So when you see a carbon like this one, you can see that it has a bond of carbon on that side and that side. So that's 2 of its bonds. So the other 2 bonds are understood to be hydrogen. So that's why it has 2 hydrogens on it. All right. So now that's 2, 4, 6, and then there's one also a hydrogen here. So let's count those up. All right. 1, 2, 3, 4, 5, and then let's just double them. So 7, 9, 11, and then 1, 2, 3. So 14 hydrogens. And then of course you can see the nitrogens here and here, which is N2. Right. So this is the structure for nicotine. Right. I was telling the class this morning that this molecular formula is for nicotine, but there are other structures that can have the same formula, or other molecules that can have the same formula, but they might just have a different structure. So there might be, if it's 10 carbons, you may be talking about hundreds or even thousands of compounds that can have this exact same molecular formula, but a different structure. So there are other molecules with the same formula or different structures. We call those isomers. Right, those are what we call constitutional isomers. Right, so C10H14N2, there might be 1,000 compounds that have 10 carbons, 14 hydrogens, and 2 nitrogens, right? But they don't all have the same structure. They're all different compounds. So that's what we mean. And it takes us all the way back to that law of multiple proportions, where you have elements that come together to make different compounds, and they bond, come together in small whole number ratios, it's the exact same idea. So you got all these other compounds that are possible, but we're gonna leave that. That's something that you'll learn more about when you get to organic 1. All right, any questions about anything that we've talked about?